Okay, we're back talking about exponential applications, and I wanted to compare the exponential decay using the fraction as our b. So, for example, we had y equals a times b to the x, where b is, well, let me say 0 technically is less than b. Is less than 1, and if you have anything like this, then certainly for all these values b, you're exhibiting exponential decay. Okay, as x is increasing. And I wanted to compare this to, what if we had a negative exponent there for exponential decay? Can we do that? So consider this form, and we're going to say, let b equal c over d, which is less than 1. So essentially, I'm just fitting it into here. C over d is a fraction, so I'm just calling it a fraction. C is smaller than d because it's less than 1. Okay. Then this form looks like y equals a times c over d to the x. And there's our fraction a little bit more explicitly. Now recall from our other exponential lessons that c over d is the same thing as d over c to the negative 1 power. So I'm going to go ahead and change this to that so that we get y equals a times, I'll use the brackets, parentheses, d over c to the negative 1, and all of this is to the x, which can be also stated as a times d over c to the negative x, where d over c must be greater than 1. So now my function looks like, do it in blue, I guess. Let me just call the d over c something else. How about g? Okay. Then y equals a times g to the negative x, where g is greater than 1. This also exhibits exponential decay. So it's just another functional form. Just another way to show some kind of exponential decay, where in this case our g is some number greater than 1. Okay, so now I want to connect this with an example we did last time, that carbon-15 half-life example. So hang on a second. You can fast forward if you like. I'm going to erase this and then recopy down the data from our last example. Sometimes this is faster than other times. You have a fast forward button, you can see the magic quickly. All right. Okay. And now copying data from the last one, our carbon-15 half-life example. Half-life, where the half-life is 2.5 seconds. Here's my x and y, and we had these values: 0, 2.5 seconds, 5 seconds, 7.5 seconds, and 10 seconds. And we started with 100 for the y value, so we had 100 grams, whatever you want to call it, of carbon-15, let's say. All right, then we're going to do half each half-life. That makes sense. Okay. And now I'm just going to fit it to the functional form that looks like this. Y equals A times, oh, sorry, I said G, I called it instead of B, so we'll call it G, that's fine. Y equals AG to the negative X. And we're going to try to find exactly what the A is, exactly what the G is. Okay, so all I have to do is plug in the data if I have a table there. And so let's do that. How about this one? When Y is 100, we've got AG to the negative 0. Negative 0 is the same thing as 0. Anything to the 0 power is 1, so this just comes out to A. Therefore, so far we've got Y equals 100, G to the negative X, and that 100 corresponding to 0 makes sense for these applications. It's your initial amount, okay? So perhaps I could have simply said that right away. Now let's plug in another value to get our G here. And it doesn't matter what you choose. I think I chose 5 last time. Like I said, it doesn't really matter, so yeah, why not? Let's go with the same thing. We'll choose 5. So then 525 is my pair, and it kind of lines up with where I'm going here. 25 is equal to 100 G to the negative 5.0. I'm just going to leave it as 5 right now. Divide both sides by 100. Okay, and so on the left side we get 0.25 equals G to the negative 5th. All right, which is, this is going to be a little bit more difficult, I suppose. 1 over G to the 5th. Now, rearranging this, I get G to the 5th is equal to 1 over 0.25. Okay, actually this fraction here flipped over, which is 4. So if I take the 5th root of G on this side, I'll get G by itself. But I also need to take the 5th root of 4 over here. So I'm going to say, okay, G is precisely the 5th root of 4. I don't know exactly what that value is. Let me punch that up here on the number dealy bob calculator thingy. All right. The 5th root is the same as the 1/5 power if you want to stick it in your calculator like that. So this is about 4 to the 1/5 power, or the 5th root of 4. Oh, 1.3195, so about 1.32. Okay. All right. So my functional form then is Y is approximately 100 times 1.32 to the negative X. And if you do the graph, we did the graph last time. You could graph it from the table, or you could graph it using this functional form. Of course, the table we could say is the actual data. The functional form in this case is approximate because I approximated G. It looks like, let's check the range on Y. 100 is our maximum amount, 6.25 is our minimum amount. And I believe last time we just went by tens. 1, 2, 3, 4, 5, 6, 7, 8, 9. Need a little bit more space to do 10. Okay, and times 10 is 100, which is where I was going with that. So that'll be 100, 90, 80, 70, 60, 50, 40, 30, 20, 10. And let's check the domain. It looks like we're going from 0 to 10, so I'll just do 10 little hash marks that way. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Going by ones over here. 8, 9, 10. The x-axis is referring to time. Maybe I should have put t, and it's time in seconds to be particular. This one is amount in grams, we were saying. Our initial amount, according to the table, is right here. 100 at the initial time, 0. We just have a chunk, 100 grams of this stuff. 2.5 seconds later, we only have 50. So here's 50, match that up to 2.5. There we go, about there. 5 seconds, we have 25. So about here. 7.5 seconds, we have 12.5. So I don't know, about there. That's a pretty rough guess. And at 10 seconds, 6.25. This is going to be another pretty rough guess. Something like that. And if you connect it with a nice smooth line, as smooth as you can, it looks something like that. Gets ever closer to 0. Over here on this side, it looks kind of like this. Coming down real steep. Okay. All right, that's good enough, even though I kind of went up there at the end with my little curve. It's hard to do this by hand necessarily. So anyway, there it is. There's the example using the functional form where we have a negative exponent, which really also gives us exponential decay when g is greater than 1, just like our ab to the x when b was a fraction. So have fun comparing those two. Stay tuned for the next video. We're still going to talk about compound interest.